Hi, this is the first unit in a section on variational autoencoders. And before we start doing variational autoencoders, I'm going to review differential entropy and point out some of the difficulties and perils of differential entropy. So if you remember in Gans were used to model probability distributions over images. And sound waves and images have this property that they're continuous structured objects. And for continuous objects like an image, we need a probability density rather than a discrete probability. So we can imagine using cross entropy, which is used for discrete cases, machine translation, for this setting. But this involves, it becomes a differential cross entropy. So in the unconditional case, like modeling a distribution over images, this is our objective. We draw images from some population, and we have a model probability density over the images. Remember that GANs were also used to do image-to-image translating a photograph to a map or a horse to a zebra. In that case, you've got an input and an output. And the objective function, the natural objective function for the labeled case is to have a set of translation pairs from some population, and you're minimizing the probability density of the translation y given x. So variational autoencoders are going to more directly use a cross entropy loss, but it's going to be a little complicated. The first problem I want to point out is that differential cross entropy can go to minus infinity. So the simplest case of this is if you just take a uniform distribution on an interval. So the density of that thing is going to be higher as the interval shrinks. So in fact, the differential entropy, so this is the differential entropy, is analytically just the log of the width for this uniform distribution on a width. And as that width goes to 0, the differential entropy goes to minus infinity. So, and this is also true for cross entropy. These log probabilities can go to negative log probabilities can go to minus infinity because the densities can be larger than 1. So this cross entropy loss is minimizing something that can diverge to negative infinity. So here, another case is if the training data is discrete. So I've got a discrete set of training points, and I'm just doing density estimation. A density can put a really narrow box probability around each one of those points. And so the density at those points can be arbitrarily large. And if the density at the points is arbitrarily large, then this cross entropy loss again diverges to minus infinity. And this would actually happen in a Gaussian mixture model where one of the Gaussians focuses on one point. If one of the Gaussians is focused on one point, its variance will go to 0, and the entropy will go to negative infinity. Now you could solve this by putting some smoothness constraint on the density or bounding its local density to be less than some limit. But that would involve maybe some other regularization on the density function, and it just feels like it's difficult to control, and you don't really know if this phenomenon is happening. There's also this weird thing that happens is in that the entropy, the differential entropy or cross entropy, if you've got something that has units like feet versus meters versus miles, and have a probability distribution over distances, but I measure the numbers in different units, it's going to give me different differential entropies, right? If I take that unit interval and I measure its width in miles, I'm going to get a different entropy than if I measure its width in inches. So this just is a little disturbing. The right way to think about differential entropy is that it's actually infinite. If I take an arbitrary real number has an infinite number of bits. So for a particular point, it's carrying an infinite amount of information. So the entropy should be thought of as being infinite. On the other hand, KL divergence is meaningful. So KL divergence between two densities is always non-negative. The same proof that KL divergence is non-negative works in the continuous case. It's an application of Jensen's inequality. And you can work through various examples. It's always non-zero. It can be infinite, just like in the discrete case. But just to think about it a little bit, if I look at the KL divergence between a distribution and itself, it doesn't matter how that distribution shaped, how strongly peaked it is, how high the density gets. Completely independent of the differential entropy, this KL divergence is going to be zero. So KL divergence is meaningful. Differential entropy is dicey. It can go to minus infinity. Mutual information. When we get to variational autoencoders, I'm going to really focus on mutual information and Shannon's channel capacity theorem in the continuous signal case. Mutual information is a KL divergence. It's the KL divergence between the joint distribution and the product of marginals. So mutual information is always going to be non-negative. It is a KL divergence. So it's going to be a meaningful, friendly quantity. Just to point out, the difference between something like mutual information and differential entropy is the information processing inequality. So in the discrete case, you say, well, if I have a discrete random variable and I take a function of it, the entropy of the value of that function is never larger than the entropy of x, of whatever distribution I'm working with. That's the data processing inequality. For a continuous value, I can always scale it up or scale it down. If I scale it up, its entropy gets larger. If I scale it down, its entropy does get smaller. But the data processing inequality fails for differential entropy. However, KL divergence and mutual information are friendly, and you do get a data processing inequality for mutual information. If I've got a random variable y, and I compute a function of y, then the mutual information between this thing computed from y and any other value x is always less than or equal to the mutual information between x and y. So if you use mutual information, a function does destroy mutual or can't add mutual information with some other variable. So we want to work with KL divergences and mutual information, which are friendlier in the differential case than differential entropy. Okay, and I will stop there and we'll move on to the next unit.